is going to speak to us about rigidity and reconstruction in matroids of highly connected graphs.
Yeah. Thank you. Does this work at the moment? No? Do I have to? Does this work now? Yeah? Something? Okay. So let me just start by saying that it's a pleasure to be here. And I'm really looking forward to hearing all the talks this week. And I am a PhD student at ELTE at Budapest. If I look that way, then can you still hear me? Kind of? Okay. So, and today I want to talk about two questions that are sort of general questions about matroids defined on the edge sets of graphs. So suppose that we have a matroid mg defined on each finite graph G, on the edge set of each finite graph G. And the two questions I want to focus on are what I call the Whitney type and the Lovász-Jeminy type questions. So the Whitney type asks whether every sufficiently highly connected graph is uniquely determined by the corresponding matroid mg. And for the Lovász-Jeminy type question, we ask whether every highly connected graph has maximum rank among graphs on the same number of vertices. So today I just want to give a brief survey of some old and a lot of new results on these two questions. And I will also describe a couple of applications of these Lovász-Jeminy type results for graph theory. So I will show how they were used to solve some long-standing conjectures. And towards the end of the talk, we will also see that these two questions are more closely related than they might appear at first sight. So first, let me just explain the terminology. It, of course, comes from a pair of classic theorems. And the first is by Whitney. It's about the graphic matroid. And it says that if we have two graphs without isolated vertices and their graphic matroids are isomorphic and one of the graphs is three connected, then actually the isomorphism between the two matroids comes from an isomorphism between the two graphs. So in a strong sense, it says that three connected graphs are uniquely determined by their graphic matroid. And the second type of question is inspired by this result of Lovász and Jeminy. So this is about the two-dimensional generic rigidity matroid. In a couple of slides, I will loosely define what that is. But the theorem says that every six connected graph has maximal rank in this matroid among graphs on the same number of vertices. So for people in rigidity theory, they say that six connected graphs are generically rigid in the plane. So we will be looking at analogs of these theorems. And let me start by explaining the general setting that I want to work in. So we will have a matroid defined on the edge set of each finite graph. And we will make two rather natural assumptions. One is essentially that this family of matroids is well defined, so isomorphic graphs get the same matroid, and that they are compatible with respect to taking subgraphs. And this is what I will call a graph matroid family. So if you like infinite matroids, this is essentially the same as taking a finitary matroid on the edge set of the countable complete graph and requiring that the matroid be invariant to the automorphisms of this graph. So very often when you have a matroid on a graph, then you actually have a family of matroids. But this model does not include cases where you work with some decorated graphs like these gain graphic matroids. And unsurprisingly, others have already looked at essentially the same concept. So I found at least three names describing the same things, but I didn't like either of these names, so I went ahead and introduced the fourth name. And within this general family, we will concentrate on two kinds of examples. One of them is the family of count matroids. Oh, no. Yeah, I'm not yet there. So first, I just want to fix some basic terminology. That if we have such a family of matroids, we say that a graph is independent with respect to this family if its edge set is independent in MG, and it is rigid if it has maximum rank among graphs on the same number of vertices. So if it has the same rank as the complete graph on the same vertex set. And I just want to highlight one sort of general result about these graph matroid families. So, of course, we always have the graph matroid family where every graph is independent. I call this the trivial family. And it turns out that if the family is non-trivial, then the rank of complete graphs grows linearly for a large enough number of vertices. So, and in this linear expression, the coefficient of n can be thought of as the dimensionality of the family, which measures how fast the rank grows. So this is like a homework exercise level thing, but to me it was surprising or not intuitive that these graph matroid families would automatically have so much structure. And so, as I said, we will consider two main examples. One is the count matroids. So these are defined using a pair of parameters k and l. And we say that a graph is KL sparse if every subset of vertices of size at least 2. If we look at the number of edges this set of vertices induces, it's at most k times the number of vertices minus L. So it's a sparsity condition. And it turns out that this defines the independent set of a graph matroid family, which we call the KL count matroids. So this includes a couple of well-known matroids, the graphic matroids, unions of graphic matroids, and also these bicircular matroids. The other main family is one I mentioned, these generic rigidity matroids. And I will not have the time to properly define these. So I will just give the intuitive picture, which is that you take your graph and you embed the vertices into d-dimensional space. And you look at whether this embedding can be continuously deformed so that the edge lengths are kept fixed. And if for generic, whatever that means, embeddings, you cannot do this deformation, then you say that the graph is RD rigid. And this RD is actually one of these graph matroid families. So the standard example is thinking about the force cycle in the plane. It's easy to convince yourself that for most embeddings, if you embed it into the plane, it has this kind of flopping motion. The embedding is usually not so symmetric as in the picture, but it has a similar motion. And if you add this extra diagonal edge, then only the trivial motions remain. So this graph on the right is R2 rigid, but the force cycle is not. Okay, and so we will actually really not need the exact definition. What we will only use is that this is indeed a matroid and that RD rigid graphs on at least d plus 1 vertices are always d vertex connected. So this is easy to verify from this intuitive picture as well. And I want to know that in low dimensions, dimension 1 and 2, these are in fact count matroids. But for higher dimension, they are not count matroids, and it is a major open problem to actually understand these matroids. Okay. Any questions so far? Yes? Sorry? So it was the notation, I didn't explain, but it was the notation for these count matroids. So the count matroid has these two parameters. And what I'm saying here is that the rigidity matroid in one dimension is this 1-1 count matroid, which is the graphic matroid, by the way. And the two-dimensional is this 2-3 count matroid. Is that okay? Okay, so let's get to these. The first group of questions that I want to discuss, these Lovász-Jeminy questions. And so by a Lovász-Jeminy type result, I will mean a statement of the form: every sufficiently highly connected graph is rigid with respect to some family of matroids. And for count matroids, we have a number of classic results in this way. And so M11 count matroid is the graphic matroid. For it to have maximum rank, that's the same as saying that the graph is connected. So there, by definition, we have a Lovász-Jeminy type theorem. And this M10, that's the bicircular matroid, for those who know it. There, it's easy to see that rigidity with respect to this matroid means that every connected component of the graph contains at least one cycle. And so for these two, connectivity is sufficient, but actually it's enough to have a degree at least 2. So MKK, that's the k-fold union of the graphic matroids. And there we have a classic result due to Tutt and Nash-Williams, which says that in a 2k edge connected graph, you can find k edge disjoint spanning trees. And that's actually essentially the same as MKK rigidity. So here we have the 2k bound, and actually edge connectivity suffices. And also, so the theorem of Lovász and Jeminy says that 6 connected graphs are M23 rigid. So what this slide shows that already for count matroids we have quite a large variety of different results. And one of our original motivations was to just understand this phenomenon for this class of matroids, so for count matroids. And eventually we did. So last year with Tibor Jordan and Csaba Király, we gave a general result of this type for count matroids. And the main point is that it turns out that there are 3 distinct regimes for these count matroids. If the parameter L is at most 0, then it behaves like the bicircular matroid. So actually a minimum degree requirement is enough. And if L is between 0 and k, then it behaves like the union of graphic matroids. So actually an edge connectivity requirement is enough. And the difficult case is when L is larger than k. So this is what most resembles the original Lovász-Jeminy proof. And what we did was an adaptation of that proof, but there were some significant tricks involved. So this is like the warm-up, and now let's think about these rigidity matroids. So when Lovász and Jeminy proved their result, they also conjectured an analog of this for higher dimensional generic rigidity. They conjectured that D times D plus 1 connected graphs are RD rigid. And they also showed that if true, then this would be the best possible bound. And for 40 years, this has been one of the central unsolved problems of rigidity theory. Until last year, out of nowhere, came a master student, and he gave an amazing proof of this. So the proof is really very elementary, but extremely tricky. And I would say it's the kind of proof that you would expect Lovász to have done 40 years ago, but he didn't. So now we know this, and one of the interesting features of this proof is that it barely uses anything concrete about the rank function of the generic rigidity matroid, which is unsurprising, as we do not have a good characterizations for it. And maybe because of this, it turns out that this proof method can be generalized much further. So the first thing we did after Soma-Villani came out with his proof, we started working on it together and started by considering the k-fold union of rigidity matroids. And in a moment, I will tell why this is interesting. So we could pretty quickly see that his proof can be adapted for this matroid, which I will denote by RD to the k. And it gives a Lobachia-Mini type result with bound roughly this size. And by using some other tricks, or actually another but similar approach, we could improve this dependency on K. So we have that every K times 10 times D plus 1 connected graph is rigid in this weird family of matroids. So why is this interesting? I have two applications for this. And for one of them, the point is that these RD rigid graphs are deconnected. And it is easy to see that if someone is rigid with respect to this union of matroids, and it has enough vertices, then it must contain K edge disjoint RD rigid spanning subgraphs. So as a corollary to this, we get a packing result for deconnected graphs. We get that every sufficiently highly connected graph contains K edge disjoint spanning deconnected subgraphs. And actually this was open even in the special case when K is 2. And even in the more special case when we are just looking for an edge disjoint deconnected graph and a spanning tree. Spanning deconnected graph and a spanning tree. So this very special case was conjectured by Kriesel, and I think that this is a nice application of matroid theory to like classical graph theory. And the other application is an answer to a conjecture of Thomassen. We said that for every K, every sufficiently highly connected graph has an orientation such that the resulting directed graph is K vertex connected. So what we could show is that if a graph contains two R4K rigid spanning subgraphs, two disjoint, then we can use that to construct by hand an orientation like this, a K-connected orientation. And then if we combine this with our previous Lobachia-Mini type result, we get that Thomassen's conjecture is true with a bound on the order of K squared. But here the constant factor is really too large for this to be useful in practice. So these are our applications. And to round off this discussion about the Lobachia-Mini type theorems, I will just quickly show how far the proof method of Villani can be taken. So it turns out that we can prove a rather general Lobachia-Mini type result for these graph matroid families that I call extendable. So recall that we had an invariant called the dimensionality of the family, which measured how fast the rank grows. And I say that the family is extendable if independence is preserved by a certain graph operation, which is this edge split operation that you take an edge, you subdivide it, and then add d minus 1 extra neighbors. And it turns out that the original proof of Villani can be used to show this general result that every graph matroid family that is extendable has this kind of Lobachia-Mini result. So here I do not care about the exact bound that I get, so I just say that a graph matroid family has the Lobachia-Mini property if every sufficiently highly connected graph is rigid with respect to it. And so this includes all of the previous results and I think many others that you could think of. But the constant we get from this proof is usually far from best possible. And I just want to emphasize that the content of this proof comes from ideas of this master student, Villani. Actually, he's now a PhD student. And all I did was just see how far that proof method goes. Okay, so that's it for these Lobachia-Mini type results. And in the last few minutes, I want to describe how these relate to the Whitney type results that I mentioned at the start of the talk. So first, let us define what it means exactly to be reconstructible from a matroid. It's what we saw in Whitney's theorem. So it means that if we have another graph with an isomorphic matroid, then the isomorphism between the matroids must come from an isomorphism between the graphs. And what it means for an isomorphism of matroids to come from the graph isomorphism, you can figure that out easily. And also, we want to exclude isolated vertices here, since the matroid is defined on the edge set, it cannot see isolated vertices. So this is what I call an M-reconstructible matroid. That's good. It's time. I have like 3 minutes. Okay, but I can just run. I know. So, okay, for the sake of 3 minutes, I will skip this. It's just our original starting point that for count matroids, there are a number of reconstructibility results in this way. And we could generalize this to all count matroids. But a few months ago, I realized that the proof we gave for this is not the right proof, and in fact, the statement is not the right statement either, because the right statement is this very general-looking thing about graph matroid families, which says that an unbounded graph matroid family has the Lobachia-Mini property if and only if it has the Whitney property. So unbounded means that the rank grows. Rank is unbounded. There's no absolute constant bounding it. The Lobachia-Mini property was that every sufficiently highly connected graph is rigid, and this Whitney property is that every sufficiently highly connected graph is reconstructible from the matroid. So I'm still very surprised that such a general result holds. To me, this is not intuitive. And then, just to round this off, for me, the two takeaways are that these Lobachia-Mini type and Whitney type results are closely connected and in a quite general setting, and hold for many of these matroid families. And that Lobachia-Mini type results for interesting matroids can have interesting graph theoretic applications. And this is an area where it's very easy to generate new questions. And on the slide, I've put some that I find interesting. So thank you.
Are there any questions for Dániel? Yes.
For the basic rigidity, the generic rigidity matroid, it is tight. Yeah, but for the union and also for this packing of deconnected spanning subgraphs, it's certainly not tight. Yes. You mean like? Can I decide, if you give me a family of matroids, can I I think it's a good question, but I have no idea about this. So to me, it seems like this whole notion of graph matroid family is surprisingly unexplored. So I listed a couple of papers at the start in small type, but these are really just some basic properties.
All right, I think we should save further questions for the break, and then we'll start again at 2:40.